All right, everybody. This video is for the lesson 10-9. We're going to be talking about infinite series today, meaning it goes on forever, and how to find that sum and deal with that stuff. So again, as you're going through this, I would encourage you to watch each example. There's a different formula here than we've used in the past, so if you feel like you want to try this, you can, but I would just double check after each example, making sure you're doing the right stuff. And feel free to write along with me, and then pause, rewind, and all that kind of stuff. All right, so example 1, it says, imagine you throw a ball into the air 10 meters, and when it comes back down, you let it bounce. It has a bounce ratio of 60%, meaning it bounces 60% of its previous height. Find the total distance the ball has traveled up and down if you let it bounce 15 times. So basically, you're throwing a ball up in the air and just letting it drop and kind of, ricochet back down. So just to kind of make sure we understand the situation, we're throwing it up 10 meters. So just a quick, very bad drawing, but so it goes up 10 meters. Now it's going to come back down and hit the ground at 10 meters, right? Or come back from wherever you threw it from 10 meters. So what's going to happen the next time after it comes back from the ground, it's only going to go up 60% of the first distance it went up, right? So 60% of 10, or if I multiplied by 0.6, that means it's only going to go up 6 meters. So it goes up into the air 6 meters. Well, it's going to have to come back down. We're going to assume it comes back down also again at 6 meters. And then the third bounce, it's only going to go up 60% of this. Right? So if I multiply 6 times, if I change this into 0.6, if I make that percentage into a decimal, that's going to be like 3.6. So it's going up. My arrow should be trying to make them be smaller each time, but it kind of started them a little too small. And down 3.6. So just so you understand the scenario of what's happening. So this ball is traveling up, but it's also traveling back down that same distance each time. And it's getting shorter and shorter. So if you go up in the air, it's going like boom, 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 like that, right? So we want to figure out how far does it bounce up and down together, the total, if we let it bounce 15 times. So this might seem familiar, hopefully. This is actually like a geometric series happening. So if I were to write out all these distances for 15 different bounces and add them up, that's really what we're finding here is the total, right? So our first number represents the first bounce. So it went up 10 and down 10. So actually that's like the first number is kind of like 20. It went up and down 20 meters total on that first bounce. Then the second bounce, it went up 6, down 6. So that's kind of a total of 12 right there. Right? And then it went up 3.6, down 3.6. So that's like 7.2. And then, goes on until we get through 15 times. So just so you understand what is happening. So to find the total distance, that is going to be the sum, and again, this is multiplying by 0.6 each time, so it's going to be that geometric sum. So remembering that from our last lesson, we're going to have the first term, which we might write as a sub 1, times our multiplier, raised to the n power, minus the first term, all divided by the multiplier minus 1. Okay, so just plugging our stuff in where it goes. For our sum, our first term again represents the entire distance up and down, so it traveled 20 meters altogether on the first bounce. The multiplier, it's only going 60% of how much it traveled the first time, so times 0.6. Raised to the n power, that means we want this to go 15 times. There's 15 terms if I were to write these out. So our n is 15 minus the first term divided by the multiplier minus 1, right? So when you're typing this in your calculator, hopefully you're getting some practice with this. I'm going to show you, I got my little 84 right here. Let me see how I can move this over. There you go. I'm just going to type in the top and then kind of deal with the bottom. So I'm going to do 20 times 0.6 raised to the 15, an arrow over so it's not in the exponent anymore, and then minus 20. So that's my top, so kind of crazy looking there. And I'm just going to keep that number. Don't round anything yet. If you're typing in things one at a time, definitely don't round it. And I'm going to divide this by, I'm going to put it in parentheses my denominator. Or you could just subtract this and type in that one particular number, but I'll put in 0.6 minus 1 in its own little parentheses. So that means that's all connected together. That's divided by all of this amount. And I get 49.9674, blah, blah, blah. So it doesn't say how to round it, but for our purposes, I'm not going to quite round it up to 50 yet. Let's say 49.98 meters. Right? And that's the total distance each time it travels up and down if it were to bounce 15 times. And if you think about it, the first bounce is 20, second bounce is 12, so altogether that's already 32 meters. It's traveled kind of in total. And each one you add is getting smaller and smaller each time. So it makes sense that this number isn't like super huge like a lot of our other geometric series and sums have been. So it's kind of a small number, right? So about almost 50 meters, but for right now we're not going to quite round it yet. So what if I were to let the ball bounce more times? Let's say we were to let the ball bounce like 100 times. So that means my only thing that would change in this equation is the exponent would be 100 instead of 15. So I'm just going to try that. All right, so I have 20 times 0.6 raised to the 100 minus 20. So I've got, it actually gives me negative 20, and then divided by 0.6 minus 1. So that actually gives us 50, maybe. Right? What if I were to let the ball bounce 1,000 times? Right? This number didn't change significantly from here, but what if I were to let it bounce 1,000 times? Again, changing that exponent really is all that's happening. Minus 20, and then divided by, oh, that's so dark, you can't even see that. And then divided by 0.6 minus 1. We're getting 50 again. So if you were to think about why is it kind of staying the same? Why isn't it getting bigger? So each time we let the ball bounce, it's adding a super duper duper tiny amount to the total. Right? Eventually in real life, the ball is probably going to have to stop because that's just how it works. What if we let the ball bounce forever? Right? Theoretically, if we were to let it keep bouncing. After 100 times, after 1,000 times, it's really only totaling up to 50. So what if I were to let it bounce forever, you know, in quotation marks here? Is it going to become a lot more than this 50? Right? So as we see, as we've increased this exponent, it hasn't really changed our sum. And what we're going to actually do for geometric series that go on forever, or that are infinite, is we're going to have a slightly different sum formula. Okay? So our sum formula, if it goes on forever, if it is an infinite series, is going to be the first term divided by, it's a slightly different, 1 minus the multiplier. Okay? So just writing it in like words for us, first term, 1 minus the multiplier. So this only works when it is going on forever, infinite, and when it is multiplying. And there's one other key characteristic we can use this sum formula with. Only when we are multiplying and the numbers are getting smaller and smaller each time in our series, right? If I were to be multiplying instead of by 0.6, let's say times just regular 6, these numbers will be getting bigger and bigger and bigger, and finding the total is going to get bigger and bigger and bigger every time. Whereas when I multiply by something and it gets smaller, that sum isn't really going to be adding too much more every time. All right? So let's try this infinite sum formula and see how it compares to letting it bounce 15 times, 100 times, 1,000 times. Our first term is, again, that first bounce. The up and down total here is 20 over 1 minus our multiplier. Okay, so 20 divided by 1 minus 0.6. We get 50. So, right, what's happening here? Why do we get the same thing? Like I said before, we are adding such a tiny amount each time we let this bounce. Forever is a pretty long time. Right? So it's bouncing and only adding the teeniest little bit of numbers. So it's really not adding much to our total. The reason we probably got 50 for these ones is because my calculator couldn't have enough digits as it needed to, right? So there's only so many digits that can fit on the calculator. I rounded this just so I didn't have to write a bunch of them out. But this probably wasn't exactly 50. It was probably 49.999999, whatever, okay? But it kind of all comes down to 50-ish for this particular problem. Okay? So we can only use this when we are multiplying by something between 0 and 1, right? Because that means it's multiplying and the numbers are getting smaller each time. If I were to multiply by 2, this gets doubled, and our sum just keeps getting bigger and bigger. There's no way to calculate it. But if we multiply and our numbers get smaller, the amounts we add are just so insignificant, it doesn't really change our total at all. Okay? So that new formula we're going to use here, it's pretty short, but it is important that you don't mix these up for the regular geometric series. So number 2, find the sum of the geometric series 81 plus 27 plus 9 plus 3, and this dot 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 is going to signify that it's going on forever. Okay, so we had some dot dot dots before, but we either told you what the end number was or there was an end number here. So if it's just this dot dot dot, that's going to mean it's an infinite series. So we're going to use our sum for an infinite series equation. We need to figure out what it's multiplying by. I can see that it's going down, so hopefully it's doing the same thing every time. Hopefully it's multiplying. So to get from 81 to 27, or to get from 9 to 3, right, or any of these, I could divide by 3, but we always want to think about in terms of multiplication. So I could actually multiply by 1/3 for all of these. Right? So that fits within our criteria here, that it has to be between 0 and 1. So I'm going to plug this into my formula. The first term, 81, divided by 1 minus my multiplier. I would not recommend writing this as a decimal, just because you might be a little bit off, because that 1/3 does go on forever. So I have 81 divided by, on my calculator, I know 1 minus 1/3 is 2/3, so I'm going to put that in its own parenthesis, 2/3, like that. Right? So that parenthesis includes that 2 and the 3 together. So it's just taking 81 divided by this quantity. And we get 121.5 is our total. Right? If we were to add all these numbers, if it continued forever, even if we just add the first 4 together, let's see, if I add the first 4 together, that's already 120, right? So what's happening is we're adding such a little amount each time, it's not really changing that sum too much from where we already are in the first 4 numbers. Right? Because it's just getting smaller and smaller. All these little bits that continue on forever are just so tiny. Example number 3 is just kind of given something in the summation notation. Find the sum of the geometric series. So how you might know it's an infinite series, if it's in this notation, is this infinity symbol up here. Right? So that means there's an infinite amount of terms, and it's not going to make sense for you to plug in infinity up here. Right? That's kind of silly. So we use this other formula. We use that infinite sum formula. So just be careful. This equation, I'm seeing a lot of my students messing up the stuff with summation notation because we're tricking you kind of on purpose. This formula here is not in first term form. Right? It's in first term form if there's an n minus 1 in the exponent. So when you're asked to find the sum, whichever equation it is, all of them really, you need the first term. So if you're assuming, oh, hey, that's the first term, it's really not. So make sure if you need to find the first term, plug in this number, n equals 1 for the exponent, and that will be sure to tell you the first term. Because it's not always just this 5, because this equation, again, is not written in first term form. So I'm going to plug in 1 in my n spot in my exponent, so 5 times 2/5. Those 5s would cancel out. Actually, my first term is 2. So just be really careful, especially when you have this sigma or the summation notation stuff. A lot of people are are not paying attention to what format the equation it is. It's not always in that first term form. However, this is going to be an infinite series. It starts with a 2, right? I can assume my multiplier is 2/5, but again, let's see if we're not sure about that. The second term, we'd find by plugging in a 2 in our exponent. All right, so we get 5 times 4 25ths. That's going to give us 20 25ths. If I divide both of those by 5, we get 4/5, right? So how to get from here to here? If I times by 2/5, yep, that'll get us there. So that kind of confirms our multiplier is 2/5, and it is less than 1 and bigger than 0. So we can use this sum formula. So our first term's 2 over 1 minus 2/5. All right, so and again, depending on your calculator, I'd probably go ahead and calculate this part first. This one, the fraction doesn't repeat, so that's kind of good. So I have 2 divided by 3/5 gives me 3, 3, 3, 3, 3. So we can say 3.3 repeating, or on my calculator, there's this little button, math button, and the first one, fraction, and that converts it to a fraction for you. So you could write it as 10/3 would be our sum. Either of those is okay. All right, we got 2 more to go through here. I've got practice problems. Question number 4. Write the repeating decimal 0.63. The 63 is what's repeating. Write it as an infinite series and then find the sum. All right, so an infinite series. So a series means a list of numbers, with the plus sign. Infinite meaning it's going on forever. So if I were to write this out, right, this really means 0.636363. 6 threes just keep going. Right? That's not a series, that's just expanding what this number really means. Okay? So an infinite series, we need a list of numbers. So what's going to happen here is we're starting with 0.63. That's kind of like our base here. We got those 2 numbers are what's repeating. Now if I were to add something to this to try to get the next piece here, let's just focus on it's repeating every 2 numbers, right? So if I have the first 2 numbers, how can I get these next 2 numbers to be added together to start to create this? I'm going to have 0. I have 2 spots here that need to be kind of like placeholders. I need to add this number with 0.63 to get 0.6363. So I'm going to have 2 placeholders, and then this is the repeating 63 right here. And if I added those 2 together, I should get 0.6363 so far. Right? Now what if I want to get that part of it? I'm going to have to add another number. So I'm going to have 0. I'm going to actually have 4 placeholders. I've kind of gotten these 4 numbers put together so far. And then I'm going to have that 63. So if we added these 3 terms together, we're getting closer to this infinite repeating decimal. Okay? So this is our infinite series, and it's going to obviously keep going. But we have these placeholders because if I add these together, the first 2 digits come from this 63, then these carry on the next 2 digits, and these are the next 2 digits in our entire big decimal here. So hopefully that makes a little bit of sense of how to write it as a series. But what we're going to do now that it's an infinite series, we're going to find the sum. So the sum is the first term, which was the 0.63. That was just the part that was kind of repeating. Right? And then we're going to divide it by 1 minus our multiplier. Well, how do we get from here to here? What would we have to multiply? It's definitely something with a decimal. We could just do a little trial and error maybe. Right? But if I did 0.63 times 0.01, that gets me to that next term that I had here. And if I do that again, times 0.01, oops, mine doesn't show, but maybe your calculator does. But that means my decimal place is moved over 5 spots to the left, which would be the same as this next term here. So my multiplier is going to be 0.01, and there's an easy way to find this out. It's pretty much going to always be something with a point and a 1. The key is how many zeros are there, right? So it's going to match however many terms are repeating here. So I have 2 terms repeating. I'm going to have a 0 in the first spot, and then I'll have the 1 on the second spot, or the end spot. Right? We'll look at another example where maybe there's like 3 repeating terms. That means our multiplier would be like 3 digits long, and it's going to always have zeros and an end with a 1. Okay, so hopefully that makes sense. As you practice, you'll get better. Then from here, we just calculate this. And the kind of cool part is that you can really do this without a calculator, right? You can type this in the calculator, but if I have these decimals and they're both in the same like decimal place value like that, I can almost just kind of forget about those and say this is really like 63 over 99. Right? And if I were to simplify that, let's see, both of those can be divided by 9. I'm going to get 7 over 11. Okay, so that's the sum. If we were to add all of these together, it would add up to be about 7/11ths. And what's cool about this is this 7/11ths is this as a fraction. Okay, so if you have to change this repeating decimal into a fraction, sometimes you're able to do that with a calculator. Sometimes it doesn't really work out great. So we can find the sum, and assuming this is an infinite series, and get the equivalent fraction from the repeating decimal. Okay, so this one's a little bit weird. I get it. I think hopefully after we do the next one, you'll feel better about it. Okay, we got one more to practice this idea again. And then we got some practice questions. So example number 5, change the repeating decimal into a fraction. So basically, we're going to find the sum of the infinite series. And that's how we will find out what the fraction is. So we have our first term. If I were to write this out, let me write this out into like a series first. So I have 0.143, That's just what this number means, a shorthand version of it. So if I need to split this up into different like pieces that end up adding together to be this, my first term would be just the kind of basic, the part that's repeating, 0.143. Right? So that takes care of the first 3 digits. Now I need to add something to that that will get me the next 3 digits. So the first 3 digits are already accounted for. So that means I'm going to have 3 placeholders and then the next 143. Right, so that gets us through the first 6 digits. So I have the first 6 digits accounted for, so I'm going to have 6 placeholder zeros. 1, 2, 3, 4, 5, 6, and then another 143. So that gets us through the first 9 numbers, right? It's going to keep continuing like this if I added more. So this is our infinite series. So we're going to find the sum here. So our first term is just this part that is basically the repeating part, right? Before it repeats over again. So here's our first term divided by 1 minus the multiplier. So what I said on example 4 is it's always going to do something with like a point and a 1, and there's going to be some zeros in it. And it's going to match how many decimal places are repeating. So there's 3 decimal places repeating here. So we're going to have a multiplier that's 3 decimal places, and the last one's going to be a 1. So that means it's going to be 0.001. You see how there's 3 decimal places there, there's 3 decimal places here, and our last decimal place is going to be a 1 all the time. Okay? So hopefully you're making a connection there. If we had a question where it says multiplying by 0.2 repeating, or I'm sorry, that's the decimal we need to find the total of. The multiplier would be just 0.1 because there's only 1 decimal place, so we've got to have that 0.1. If it was 0.1358, that whole 4 digits repeating, our multiplier would be 0.0001. So you see how there's 4 digits, and the last one is the 1. Okay, so it's pretty easy to figure out once you kind of see what's happening with this repeating decimal. All right, so again, we can do this with a calculator, but we can also do it without a calculator. There's just going to be 1 less decimal place here than 1 every time. Same thing that we had before, 143 really over 999. And if we can simplify that, we can. That one does not simplify at all. Okay? So this is the sum, if I were to add all of these numbers together, but it is also the equivalent fraction to that repeating decimal. Okay, so the next, I have 5 questions here to practice. They're all kind of linked back to those examples. So I would encourage you to try those on your own. Go ahead and pause it and then check back and see if you need some help walking through those. So onto the practice. All right, so just like these examples. Question 1, Mrs. Green, that's supposed to be me, wants to hike around Hocking Hills on the first day of summer, and I walk 10 miles. That's probably a little ambitious right now since I've got a growing belly, in case you didn't know that. But she couldn't keep up that pace and walked 15% shorter each day. If she could walk forever, theoretically, right, maybe adding some little quotation marks here, how far would she go? So, first thing we need to figure out is it's going on forever, so that's an infinite series. We want to know the total distance walked, so that would be the sum. Right, so we're going to do the sum of the infinite series, so that's the first term over 1 minus the multiplier. So we need to figure out what's the first term. All right, well, the first day, it says I walked 10 miles over 1 minus the multiplier. Okay, this time, this is like the ball question on the front. However, our multiplier is not just 0.15. Right, I'm walking 15% less each day. So I'm really walking like 85% of what I walked the previous day, right? So our multiplier actually has to do with this 85. So it's like 0.85. So you just gotta think about the situation. This number, this percentage might not necessarily be have to do with the multiplier every time, right? So it's like I'm taking away 15%. So way back in Algebra 1, we started with kind of 100%, and it was decreasing 15%, so that's how we get the 85%, and then change that into a decimal. All right, then we just type this in the calculator. 10 divided by 1 minus 0.85, all of that's in the denominator. I'm going to get 66 2/3 miles. Right, so if I were to walk 85% of what I had each day, it's going to start out with 10, but then obviously, it's getting shorter each time, so it's not going to be like a bajillion miles, right? It's not getting super big. So you can write it as 66 2/3, you can write it as the fraction, you can write it as 66.6 repeating, that's fine. Okay? Practice question number 2. Find the sum of the infinite series 88 plus 42, or plus 44 plus 22, and then again this ... means that's going on forever. That's going on infinitely. So we want the sum of the infinite series. That's our formula right here. This one's kind of more straightforward, hopefully. First term is 88 over 1 minus our multiplier. How do I get from 88 to 44? Well, that's times half. Pretty easy. Okay, so I really have 88 divided by a half. Or, again, doing this without a calculator, if you felt like it. These cancel out. I'm left with 88 times 2, which is 176. And that's not like units or anything. Right? And again, this is if I added these together. If I add just the first 3 together, that's already 154. So the next one would be 11. Then the next one would be 5.5. So it's adding a little bit more than the first 3, but it's not getting a ton bigger because everything we're adding is getting smaller and smaller as we go on forever. Okay. Number 3, find the sum. All right, this one's got that summation notation, and this infinity symbol here tells us that's an infinite series, so we're going to use that same sum formula. So we want the first term. Now, this one is in first term form because I have this k minus 1. So that means this is my first term. This is my multiplier, but just be careful because it's not always in first term form. If you want to be sure, plug that number right here in the exponent, and that will tell you the first term. I have 25 times 1/5 raised to the 1 minus 1 power. We have to follow the order of operations. We would get, 1 1/5 to the 0 power, we do that first. That's really worth a 1. 25 times 1 is just 25. So again, confirming 25 is our first term. And then we do 1 minus our multiplier, which is going to be 1/5. If you weren't sure if that's the multiplier, plug in a 2 up here and then see the difference between the first and second term. All right, so we have 25 really over. I'm going to type it in as 5/4. And again, you could do that as a decimal if you prefer. We get around 31.25 is our total. All right, so it's being multiplied by a 1/5. We start with 25. That's the biggest number we have. Then it's going to get a 1/5 smaller each time. So it's not adding too much more. Okay. Number 4 is another sigma notation with the infinity at the top. So we're going to use that same sum formula. However, this one is not in first term form. So again, just be aware, our first term is not 600 here. If it was in first term form, we'd have an m minus 1 or whatever variable minus 1 up there. So just be careful. So I need to find the first term. I'm going to plug in whatever number is down here. This might not even be a 1, but plug in whatever this number is first into your exponent. So I have 600 times a half, really, because raised to the first doesn't do anything. So my first term is actually 300, right? So my sum is starting 300 is my first term, 1 minus my multiplier. So 300 divided by half is really like 300 times 2, so 600 is my total, right? So if you are not paying attention and use 600 as the first number, it's going to be way too big because the total is actually only 600 altogether, right? 300, then it would be 150, then it would be 75, and then continuing on from there forever. Okay? So just be really careful when you do this summation notation. That's the biggest mistake I think I've seen from most people. There's other mistakes as well, but that's kind of the most common one. Last question here with the repeating decimal again. Number 5, find the sum of the repeating decimal 0.56, the 5/6 is what's repeating, to write this as a fraction. So I can write this out for you, if that makes sense. You don't have to write this out, but maybe it helps some people to kind of understand what number we have. And then if I were to write it as a series, I have 0.56 is the first term, just the little first round of the repeating. So that covers the first 2 digits here. So I need to add 2 placeholders for those, and then I need the 5/6 for the next, the 3rd and 4th decimal place, right? Then I have these first 4 places covered, so I'm going to have zeros in all of those spots. And then this 5/6 covers the 5th and 6th decimal place. And it would just keep going like that, right? So that's the series. How do we find the sum of this series? So I have my first term, which is the part with before it repeats a bunch of times, over 1 minus my multiplier. Remember, my multiplier is going to match however many repeating digits I have. So there's 2 digits, so my multiplier is going to be 2 digits, and it has to end with a 1. So we're going to have 0 and then a 1. Okay? And you can obviously very easily find that. You can multiply it by 0.01, and you should get from one term to the next. So if you want to check and make sure, that's all good too. 0.56 over 0.99. So I'm going to change it into just 56 over 99, and I don't think that can be reduced at all. There's something pretty good on this calculator. If you just do, what was it, 56 divided by 99, it gives you a decimal. It gives you basically that repeating decimal. It does stop eventually because, again, there's only so many digits that the calculator can fit on the screen, right? This would just continue being 5656, but then again, that math button, and that'll tell you if it can simplify at all, but that one doesn't. Okay. So hopefully that makes sense. Sorry, this one's kind of long. It's pretty simple, but just wanted to give you some explanation on lots of different practice problems. So again, reach out to your teacher if you still have questions.